So I'm going to rename this create initial. And we only want it to operate on the first frame, otherwise the solve type is always going to be set to 0 at every frame, and so on. And we can do that using this activation parameter. And if I put a small expression in here, $sf, which is the simulation frame, so that's the equivalent of $ff, but inside a dot network, equals 1. So that will ensure that this node is only executed right at the beginning. The next thing I need to do is create our acceleration data. And I'm going to need another modified data. And I'm going to create our acceleration data again in point position. And I'm going to call it accel. And I'm going to need quite a complicated expression here to bring in our acceleration. So let's maximize this. I'm going to use a length expression, and a length function takes 3 components, which are the x, y, and z of your vector. And in this case, what I want is the length of the current velocity. So that is going to be found using the dot option. And we've got our current velocity is in our point position data, and it's vel here, and old velocity is old vel. But if you remember, the dot option function only allows you to bring in a single value, and here we're going to need to access 3 values. And Houdini achieves this by having 3 variables, velx, vely, and velz, defined automatically for the 3 components of this. Or I should say 3 fields are defined with the names velx, vely, and velz rather than 3 variables. And similarly, old velx, old vely, and old velz allow you to access the 3 components of this. So we want our dot option, $.net, $obj ID, then the point position is the subdata name, and then we're going to bring in velx, which is the current velocity in the x direction. I'm going to select that. I'm going to Control-C and then Control-V to copy it, and then the next one is going to be y, and then again paste it the second time and velz. So that's the acceleration of the velocity, the length of the velocity at the current frame, and then old vol. So we want a second length expression, and we want to access old vel, and I'm going to just Control-V again, and we want old vel x, and copy this, old, and we need to convert this to old vel y and old vel z. So what we've got here is an expression which gets the length of the vector of our current velocity and takes away the length of the vector which is our old velocity. Now that's not strictly speaking the same as calculating the acceleration, but for our purposes that's what we want. So let's minimize that and have a look at what this data looks like. I'm going to rename this create accel, or rather calc accel, like so. And the acceleration is 0, of course, at the beginning, so let's have a look at our scene. Let's press play, and when these boxes start moving like that, let's have a look at object number 95 and have a look at our point position, and we should see that the acceleration is 0 there, maybe because it's already stopped. There we can see here that the acceleration is 4, and then it goes like so. Now, of course, at the moment it's not really calculating the acceleration because we haven't got any value here in old vel. It's always 0. So to properly calculate the acceleration, we're going to need to copy our old vel. Of course, we're not actually getting the real value of the acceleration here because the old velocity, which we created here, is always 0 at the moment. It never gets changed. So we need to insert a modified data node here, which is going to copy the value of the velocity into the old velocity. So we're going to modify a bit of data in the point position container. We're going to modify the data that's called oddvel, and that is a 3 vector. Now, in order to extract a string that we can use to set up the value of oldvel, we use the dop option s. Now we need to start it with a backtick in order to ensure that this is evaluated as an expression rather than just as a string. And then the function we want is dop option s, which is exactly the same as dop option, taking the same arguments. And the only difference is that we don't need to specify the 3 components of velocity separately because this is going to produce a string with those 3 components enclosed in square brackets, which is going to be used to set this value. So I need a backtick there. And now what should happen is that we're getting the, and let's have a look at, in fact, at object number 95. And let's have a look at point position. And let's have a look at the acceleration of this. And we can see, oops. There we go, let's try again. So we're looking at object 95. We're looking at the point position data. I'm looking at accel, and I want to look at, and there we can see that the acceleration starts here with 0, goes up, and then becomes negative. So it's when this acceleration becomes negative that we want to switch to having an RBD simulation rather than the animation. So as the first stage of doing that, well, let's first rename this to copy velocity. And what I want to do is now create a group. So group dynamic objects. And I'm going to call the group transition group. I'm going to put $OS in here so that the group has the same name. And I'm going to use an expression rather than a name-based selection for the membership of the group. So we leave this at star, so that's all objects. And then we're going to put an expression in here which selects some of those objects to be in the group. And the expression I want is going to be that the acceleration, which I can get using a dop option, is less than 0. Bracket in the right place. But I want another condition here as well. So this is going to select all the objects for which acceleration is less than 0. But this is a transition group, so it's a group of the objects which are transitioning from being animated to being simulated. So I'm going to add another expression here, which is dop option $.net $obj_id point position, and if you remember, we set up a variable called solve type. I'm going to use solve type to decide whether we're simulating these objects or whether we are animating them. And with the solve type of 0, we're going to be animating them, and with a solve type of 1, we're going to be simulating them. So I only want to make these objects a member of the transition group if they're still being animated. In other words, if the solve type is 0. So this should give us a group of the objects which we need to work on to shift them from animated to simulated. So the next thing we need to do is set the solve type for these objects that are in the transition group. So I'm going to use a modify data node, and I'm going to call it set solve type, and I'm going to call it point position, and we're going to change the value of solve type to a value of 1. But we don't want this to apply to every single object, we just want it to apply to the objects which are in transition group. Then we want to use this solve type value to select which type of solver we're going to use to solve our object. And I'm going to do this using a split object stream node. It's possible to do this using groups as well, but this is a little bit clearer visually. And what a split object stream node does is split the stream of objects coming in into separate streams based on an index value here, which is usually calculated on the basis of some data attached to the object. So if this output index evaluates to 0 for a particular object, it will emerge in a stream here. If it evaluates to 1, it will emerge here, and so on. And of course the expression that we're going to use in here is a dop option, which retrieves the value of solve type. So what this should mean is that all objects with a solve type of 0 will come through here, all objects with a solve type of 1 come through here, and we can attach appropriate servers, data solvers, to those two connectors. So let's now do that. And by the way, I've deleted the copy data and RBD solvers that we had here earlier, and that's because occasionally if you reuse nodes in a dynamics network, it can confuse Houdini and create some rather hard to spot errors. So I'm rebuilding this from scratch to ensure that that doesn't happen. So we need a copy data solver where we're copying from point position to position, and that's going to deal with the objects coming out of the first stream. And then we need an RBD solver which is going to deal with the objects coming out of the second stream. Now I could just attach these to this merge node here, but if we see that the merge node is setting up a mutual collide relationship between all of the things that are plugged in. Now that isn't going to be an issue here, but to be safe I'm going to merge the two streams of objects separately, and I'm going to make sure there's no change in the relationships. Then I'm going to feed that into the merge node here. And what we should see is that when we play the simulation, the boxes are animated, and then when they reach the point where their acceleration becomes negative, they'll start to be solved by the RBD solver. And we can see that's happening, although they seem to have a very, very high velocity and they're being thrown out quite a long way. And the next step is to look at why that's happening. So what are we going to do about that high velocity that these blocks are acquiring? Well, they're acquiring that velocity because when we switch to the RBD solver, the RBD solver inherits the velocity from the keyframed animation, and that's quite high. So what we ideally want to do as part of this transition process is set that velocity to 0, or at least reduce it. And there are two ways we could do that. We could either use a modify data node to operate on the velocity directly, but this sometimes doesn't work because occasionally within the details view within the data here you have parameters that are read-only, and modify data can get confused by that or not operate correctly. So it's better if you're going to modify a quantity which exists in one of the other nodes that you use that node to do it. And in this case I'm going to use an RBD state node, because an RBD state allows me to set the velocity explicitly. So if we have a look down here, we can apply the RBD state node only to objects that are in the transition group. And in fact, in this case, I want to operate on the position data directly, because if we're dealing with objects in the transition group, the point position data is no longer going to be copied, because they're in the transition group, their solve type is going to move to being the RBD solver, and this copy data solver is not going to be called again. So we need to modify the position data directly, and we can set the velocity to 0, and I can have set always, and that should ensure that for the objects which are in the transition group, the velocity will be set to 0 before the RBD solver takes over. Let's have a look and see whether that works. So they're being picked up correctly, and the RBD solver started, and we can see now that it's no longer inheriting the very high velocity that it was earlier. So that's an example of how to combine some quite sophisticated point-based animation with dynamics. I hope you found it useful.